Hello everyone, welcome back to alkaline hydroxide 784, and today in the physics series we are going to cover the forces, I guess. Yep, let the force be with you. And sorry. Yeah, let the mass times acceleration be with you. Okay, never mind about the terrible, like the overused joke, I guess. Let's just get into the topic, I guess. Alright, so yeah, I'm just gonna look at the learning outcomes, and I'll just tell you what you should know, obviously, and what else you should probably know as well. All right, so uh, um, okay, right. So the first, why is the first one already about like the Hooke's law? I thought you're supposed to start with stuff like weight, gravity, like sorry, normal force and stuff like that. Never mind. I'm just gonna go it in the order that I like, I guess. Okay, so what's the first thing that comes to your mind when you say force? Star Wars? Well, I guess that's one thing that can come to your mind. But apart from Star Wars, the other thing that can come to your mind is of course physics. Well, because that's the only other place you hear about forces, do you? Or maybe about impacts in the economic market or something. I don't know. Anyway, that's not the point. The thing is, the definition of a force, as we heard previously, is that it is you know it is the, what can I say, the derivative of momentum, I guess. If you differentiate momentum, you will get force, and in that sense you you would see that force is equals to dm over dt times v, and plus dv or dt times m. But most of the time m doesn't really change unless you're doing some nuclear reaction or something, I don't know. So in the sense we simplify it to dv or dt times m, which is in other words m times a, mass times acceleration. And yeah, that sounds simple enough, but in reality, there's so many different places that acceleration can come from. So that's why we have so many different kinds of forces, and there's so many different ways that you can define the different forces that we see every day. Okay, so the very first force that I think everyone is familiar with is weight. You do realize there's a difference between weight and mass. So the mass of a body is absolute, like the mass of the body, I guess, the kilograms, I suppose. And the weight is actually the force exerted by the body on, I don't know, the planet, the earth. It could be the moon, Jupiter, whatever that is. And since you're all on earth and none of us are living on the moon right now, let's just say it's earth. Okay. But if let's say you're talking to a bunch of Martians on Mars or something, although I don't think there aren't really any visible Martians right now. Let's say there were visible Martians on the Mars right now, and you managed to somehow get there and talk to them. The weight, your weight on with in terms of mass, like with reference to the Martian gravity, will be different compared to your. So yeah. So what is weight? Weight is mass times acceleration once again, but this acceleration is the acceleration caused by gravity, which is, well, that makes sense. Huh? And in terms of the gravity, that we call it g, because in Earth g is 9.81, and you can calculate this value for any planet, any location, as long as you know the different parameters that are required to calculate it, which I'm pretty sure you will know if you have studied gravitation. We will cover that in gravitation itself. Okay, yeah, so just know that you need to multiply mass times g. So yeah, that's what weight is. Weight is just the force acting on you by the gravitational attraction of the body, I guess, that you're standing on. Yeah. So in this case, Earth is sorry, wait. Sorry. You are exerting an opposite force that Earth is exerting on you. So the one that you are exerting wait, no. Uh, yeah, the one that Earth is exerting on you is the weight, I guess. Wait, what? Yeah, the one that okay, never mind. The point is, when you draw a free body diagram, the weight will go away from the thing. So, yeah, let's just say that way. It confuses me for some reason. Yeah. Hmm. Like in a way, the earth is attracting you to the ground, and that's why you have a weight. You get what I mean? Yeah. Cool. Okay, so in reaction to it, you have a normal. Okay, not really in reaction, but you have a normal force as well, which is what keeps you from falling through the earth. You know, as earth is attracting you towards itself, its center. There's another force that is pushing you away from the earth center so that you don't fall and become part of the magma that the solid iron core in the middle of the earth, you know. Yeah, you don't want to be part of that. Yeah, and that force is the normal force. Well, and it is usually you usually get normal force when you contact something. Weight will always act on you regardless of whether you're in contact with the object, but normal force only requires contact. So when normal force is equals to zero, that means you're almost not contacting the thing already. So this will be useful in the chapter of motion in a circular motion chapter, and you'll find out why. Yeah. Uh, so normal force is usually about if you're just standing on the ground, it would be about the same magnitude as weight, but it will be in the opposite direction. Of course, it will be pointing upwards or at least away from the surface. But normal contact force doesn't have to be equal to the weight, because it is not exactly it is not the action reaction pair of the weight. More of it is just the force created by the contact with the surface, and it can be very different based on what kind of surface you're on and what angle you're on the surface. Okay, cool. So next one is frictional force. Wait, no, not frictional. Okay, actually, maybe frictional force, I guess. I guess that's the other kind of force that you can think of in a way. So the frictional force is usually caused by friction, of course. The Of course, you do know that there's two kinds of friction: static friction and dynamic friction. But you only see the friction, right? Like you only consider the frictional force in terms of dynamic friction, because we are just standing there, and if you're standing on a completely horizontal surface, there's no friction whatsoever. You may consider static friction maybe if you're on a slope. That is possible. Dynamic friction will be both on the slope and the flat surface if you're moving in a sense. Yeah, so the friction would technically be opposite to the supposed motion of the object. So let's say if you're looking at static friction and the slope is going downwards, obviously the static friction will act upwards, up the slope instead of down the slope, because well, there's gravity that pull the ball down in a way. And this is where the normal force may not be equal to weight, because we have frictional force as well in this scenario. And if it's on a flat surface and the ball is moving towards the right, for example, then the frictional force will be towards the left, trying to slow the ball down in a sense. Uh, and apart from friction from the ground, you can also have a air resistance or water resistance, I guess, viscous forces, and they're usually proportional to the weight of the object or to the velocity of the object in a way. So yeah, it's not very. Oh, sorry. They're usually proportional to the velocity of the object at lower speeds and proportional to the velocity squared of the object at higher speeds. That's what I remember. I hope that's correct. Please check your notes. uh, yeah, but apart from that, there's nothing else really much to say here because you don't really know the coefficient anyway. Haha. So the next one is yeah. So now we've covered what weight, normal force, frictional force slash air resistance kind of force. So let's move to more interesting stuff. So let's say you have the object and you attach it to a string, a string. Then what happens? You get the string has a tension to it, right? It has a tension. And likewise, if you put it on a spring, the spring can also experience tension and things or forces caused by the ball. So if you're looking at a string, the tension depends on the balance of forces. So if let's say the ball is just vertically hanging down and the ball only has like the main force is just weight pulling it down and it's not really moving or anything, then the tension is equal to the weight in the sense. But if the ball is being held to the side by some other string or something else, then the tension will be a different value and you need to balance it out as we will cover soon. Um, okay, and as for apart from the string, you have the spring, and sometimes if you put like a weight on it, or if you push, or if you have the spring horizontally and you push it in with some force, you need to know how much that force is, right? So in this is where Hooke's law comes in, and yeah, for the spring, not the string is a bit different because I think for the string you'd probably be more extensioning, like for extension rather than compression. For the spring, you can use it for both extension and compression. So in this scenario, the force that you're exerting on the spring, in terms of either pushing it in or pulling out, would be F equals to kx. So x is the extension or compression, the spring, I guess, and k is the constant or the force constant, which is a constant of proportionality. And you do realize that Hooke's law isn't ideal. It's like it doesn't apply to forever. There's gonna be a point where it doesn't apply anymore. Um, yeah, and at that point it will stop being proportional. I kind of forgot what is the name of that point. Uh, So if, for example, if you were to draw a graph like f and f against x, it will be nice and straight until that point, and then after that it will curve a bit, or it won't be like a straight line going in that direction. The gradient will decrease significantly in a sense. Yeah, so that's you might want to take note of that. Although you may not really be tested in it at the end of the day. So just remember that there's this point that you have to be aware of. And if you have the name, just remember the name of it. I think the point of no return. Okay, just kidding. It's not the point of no return. I think it's a different name. Okay, so yeah, that's for the string and the spring part mostly. That's for the spring. So if you get a question which has a spring in it, you might want to remember Hooke's law. Usually k is provided. They will give you a value and you can just times it by your extension if you need to. Okay, so apart from these kind of forces, what other kinds of forces can you get? Well, you can, yeah, there's this force from caused by magnets in the sense, magnetic fields, and also from electric fields and from gravitational fields. So you do realize that there are actually 3 different chapters that are after this, in a way, that cover these individual fields. Of course, the first one is gravitation for gravitational fields, and there's E fields, and there's also I don't think it's called magnetic fields obviously, but there's another one that covers the magnetic side of it. So yeah, I guess you can kind of just go and read the definitions there as well. But I will go through them once here. So the force on a mass in the gravitational field. So let's say you have two masses and they're both exerting an equal and opposite force on each other. And this force, let's say if you're standing on Earth, like the force that you're experiencing is weight, obviously, uh, which is mg. If you're looking at a more generic situation where you just have two bodies, exerting forces on each other, you can use the equation that you get in gravitation to calculate it, which is the gmm over r square, that thing. Yeah, you can just use that. For charge, um, yeah, for charge in an electric field, if you have a charge going through your wire, for example, you would, yeah, it experiences a force in the electric field, and once again you can find the value of that force using a equation, uh, big Q small q over 4 pi epsilon r squared or something. Yeah, so if you have two charges, so one charge can exert a E field on the other. So this one is for two charges. If you have just a charge and a E field, you can just you can just do the F equals to EV or something like that. The field times, oh yeah, sorry, field times the charge, sorry, velocity, B times V, what, sorry, my mind is not working obviously. Yeah, B times V, or BLV in a sense. It's also BIL, the sense BIL. uh yeah, there's all these formulas, and you can just remember those formulas and use it in those respective topics. Yeah, I'm sorry, I just can't think now. BQV, BIL, I believe. Yeah, those are the two ones that I remember. But isn't that for magnetic field? Yeah, man. I don't know what I'm doing anymore. Okay, so current carrying conductor. Actually, this is more for magnetic field, I think. BIL definitely for, wait. Yeah, I think the BQE in BIL is for current carrying conductor and magnetic field. So yeah, just use the required equations and find them. So if you just describe it, for gravitational field is weight, for electric field is the electric force, and for magnetic field is, yeah, magnetic force as well. They're all attractive forces, so just remember that. Attractive, sorry, not all of them are attractive lah. Gravitational is attractive, electric can be attractive or repulsive force, and magnetic field can also be attractive or repulsive based on whether it's, north or south pole. Yeah. Yeah, let's move on. My mind is not working. Alright, so what other forces can we look at? Oh yes, now let's just talk about upthrust, because or maybe you'll talk about upthrust later. Let me just look at the other points that I didn't cover yet in the beginning part. Okay, so let's go back to weight of a body, and you know that, you know for different objects, they have a different sense area where they balance, in the sense a different point where they balance, and that point can be considered the center of gravity. So the weight of the body can be taken to act at the center of gravity, even though it's not necessarily how it really works, but in the most simplistic sense you can take it as that. So let's say you have, because I think this is based on the idea of, you imagine like a ball, and then the center of gravity is right in the middle, and you just apply that to all the objects. You get the point. Yeah, so the most of the weight of the body will be acting at the center of gravity, and therefore if you see a question using torque, for example, which we'll be talking about very soon, you must use you must draw the weight from the center of gravity of the object based on where you know it is. If it's a uniform object, you can easily calculate it. If it's not uniform, you can see, you can try to get it from the information given in the question, or from the in terms of the pivot or something like that. You can figure out where exactly the center of gravity is. So the point is the weight of the body acts at the center of gravity. That's the important thing. So how do you use this in your talk and moments? That kind of question in the sense. Uh, Before that, let's go and cover more on talk and moments in a sense. So the moment of a force, well, what is the moment of a force? The moment of a force would be the force times times the perpendicular distance of the force from the reference point in a sense. So let's say if you have a pivot or if you have some object and you're applying a force on one end of the object, you need to have a reference point. Let's say if you have a pivot in the middle, you can consider that your reference point, and you can get the distance from the reference point to the force, which has to be perpendicular to the force. So if your force is like I don't know, diagonal or something, then you need to figure out what's the perpendicular distance from the thing to the force, not just the horizontal distance. It can be a different direction altogether. So in that sense, you need to know that, yeah, you need to figure out that perpendicular distance and maybe use some trigo in the way. I think the trigo won't be too hard, so don't worry too much about it. So in other words, yeah, the moment of a force is the force times the perpendicular distance from the reference point to the force. Yeah. So the torque of a couple. So what is a couple? Well, if you have one force in one direction, and then you just mirror the force like in the other direction and on the other side of the object, and they're both like equidistant from the reference point, then you will have a couple because they're essentially acting in the same clockwise or anti-clockwise direction for that matter, and therefore they act together. And you can find the torque of a couple by basically finding the moment for one of the forces and timesing it by 2. Then you get the torque of a couple. Okay, so yeah, which is so this couple will basically rotate the object. It won't do anything else. I don't think you can really do anything else much with the couple. Okay, cool. Uh yeah. So now let's move on to actually solving questions using this information. So let's say you have a system, and you have multiple forces acting on the system, and you also have some pivots and other points which you can use as reference points per se. So when you solve, so you might need to find some value of a force or of a distance or something like that, and in order to do that you need to use the principle of moments, which you can basically write with applying taking moments about whatever point that you're using as a reference point. So let's say, for example, if you have a seesaw and there's some people sitting on the seesaw and there's a pivot, maybe you can say taking moments with reference to the pivot, or if there's a name for it like AB, you can just use point A, point B, or something like that. And whatever forces that go through that particular point will then not be considered in your calculation because the distance is 0 from that point. So if there's anything that's passing through the point of reference, you can just ignore them in the calculation of this principle of moments because there's no perpendicular distance between that force and the point of reference in a sense. So say there's a bunch of people sitting on the seesaw, you would know that in both cases the weight is going downwards. So they're acting in opposite, they're kind of acting in opposite rotational directions in terms of clockwise and anti-clockwise. So if you look at it, right, you need to first, before you move on to applying the moments about a point, you first need to know whether the system is in equilibrium, right? So if the question mentions that, that means you can use this principle of moments and solve the problem, because equilibrium means that there's no there's no resultant force. In other words, net force is zero. And there's also no resultant torque. In other words, the moments that are clockwise and the moments that are anti-clockwise based on the reference point are balanced, and it must apply for any reference point. If you take moments from any reference point, it will always be balanced, and that's the idea of no resultant torque. So in this scenario, you would expect if the seesaw is balanced and there's no movement whatsoever, that means it is in equilibrium, and you can take clockwise moments equals to anti-clockwise moments, the sum on each side. And then if you use a common sense and see which force is likely to make it go clockwise and which is likely to make it go anti-clockwise, and then put them on the relevant side, and yeah, just apply the moment for each of them, the distance times force, blah blah blah, and then once you calculate everything, you'll get your answer. Yay, they're done. This is actually not that hard. Okay, cool. Unless you accidentally miss out something. Haha. Sorry. My throat keeps getting dry. Okay, so uh, yeah, so if you look at, so this is actually the principle of moments is more for the rotational force in the sense, in other words, torque. What about the translational force, which is just normal force on its own, without any moments whatsoever? How do you look at it in terms of equilibrium? In equilibrium, all the forces that you get, imagine them as vectors, let's say, along with the angle and their magnitude, the proportional, the relative magnitude, I say. uh, if you look at it that way, you can say that you can put like each of those forces and then connect the tip of the force to the arrow of another force, for example, and you can construct a complete shape, for example. But most of the time you will only have about three forces to look at. So this shape will usually be a triangle, let's say. And yeah, if you get a triangle, that means you can then try to find out a force that you don't originally have, in the sense like a resultant force or something like that. You do not know the magnitude or angle, but you know the other two forces, so you can use the triangle to do this. In the scenario where you have more than one force, I'll tell you another method, but before that, let's continue with this. When you use a triangle, please take note of the angles, obviously, because you need your trigo. Take note of the angles, then you can use your sine or cosine equation to figure out the magnitude of the other vector and also the angle of the other vector. Yeah, so just make sure you know the magnitude and the angles of the other two forces before you do this. If you do not want to use a triangle, or if instead of a triangle you end up getting a hexagon, which seems like too much work to deal with, you can use the other method of just breaking up all of the forces into two axes each. So like, for example, if you have a force that's going diagonally, you would have a horizontal and a vertical axis, so x and y. And likewise, you do that for all of the forces that you can see there in the diagram, and you balance all of the vertical forces, make sure that their net force is zero, and balance all the horizontal forces individually when you get net force 0. Once again, you're just using trigo again, so hopefully you should be able to do this without any issue whatsoever, and you can use a calculator if you need to. Yeah, so just do that. Right, let's move on to the next part, which is about density and pressure. Right, so what is pressure, first of all? I mean, I guess you know what pressure is. It's the thing that you feel when your exams are coming up. But apart from that kind of pressure, if you look at it in terms of as a physical quantity, pressure is the force over area, like the force applied over a certain area. And the force, it has to be, in this scenario, is perpendicular to the area that is applied onto. So if let's say your force is applied diagonally, you only consider the force that you only consider the aspect of force that is perpendicular to the area. You don't consider the one that's horizontal, because it doesn't work that way. Yeah. And for density, you would be considering the the mass over the volume of the substance. So density is kind of like how much, how much mass of a substance is there per unit volume of that substance, in a sense. Yeah, that's what it is in essence. It's just a value that people have come up with along with pressure. So in that sense, yeah, that's what pressure and density are. So this works perfectly fine for solid objects without any issue. And especially, I mean, yeah, solid objects or something like that, I guess. But if you're looking at liquid, for example, how do you define pressure? Because on the surface of a liquid is possible, because it's usually just atmospheric pressure, and you can easily define the force over an area. But if you're trying to find the pressure inside a liquid, because if you think about it, the mass of liquid above it also creates pressure on that thing. It also has a weight, that, a force acting on a point in the depth of the liquid. So if you were to look at a specific point, because we don't want to look at the area here, we don't really know the area of the liquid, we can think of it as the force of the thing on that point. And how do you get that force? Force is of the weight. It's a weight, of course. It's mg. And since we do have that idea of area, in a way, the area of the liquid, we just consider it as pressure is, F over A. Even though this area is very small here, we still need to consider it. So we write F over A first of all. And F is, of course, mg, right? Mg over A. And we know that density is mass over volume. So we do have a m here, right? So maybe we can say density times volume times g over A. So PVG over A. And volume is area times height. So we then convert it finally to PGH. And that is your equation. Pressure is equals, sorry, not P, is rho. Sorry. Pressure is rho GH in liquid, usually. Or it could also be for gas. It also works for gases. So, yeah, so now you can use this to solve problems. So let's say if you have a liquid and you're trying to find the pressure at a certain point in the liquid, so you usually will get one of those barometers or something. Yeah, just take the pressure to be whatever pressure is above the liquid. It could be atmospheric or it could be another applied pressure, plus the rho GH, based on which point your final point is at, the H from the top to the point, I guess. So you can use that to solve problems and find some answers, I guess. Okay, so the next part is about upthrust. Okay, so let's say you have some object that's floating in the fluid, in liquid, for example, like a ball floating in water. How is it floating in the water? Of course, it has its weight that's pulling it down. So how exactly is it staying in place? Maybe you could say it's like normal contact force, but in this case we have water, so what do you call it? You have upthrust. So the upthrust is basically it is kind of like a normal contact force if you think about it, but it doesn't really work for all objects. Some objects actually sink in water. So what exactly is it? Well, upthrust is kind of like the force that's exerted on the object based on how much liquid the object actually displaces by being there. So if let's say the object has certain volume and you place it into the liquid on top of the liquid, so it displaces some volume of liquid. Sorry, it doesn't displace the volume like in terms of the volume of the object, but it displaces a volume of liquid that's equal to the mass of the object. because the object will exert its mass on the liquid, right? And therefore the liquid of that mass will be displaced. And because of that, the liquid will then exert an equal and opposite force called upthrust back onto the object, I should say. Not really equal and opposite lah. That's only applicable if it floats. If the object's weight is too much such that like if the object is too dense, it will the amount of liquid that it displaces will not be sufficient to counter the weight of the object, and the object will sink. And yeah, in this scenario you end up with the sunken object, I guess. So in other words, upthrust is equal to the weight of the fluid that's displaced by the object, in the sense. So it can be half submerged or floating, and it can be fully submerged. So the upthrust is only equal to how much liquid it can actually displace, and therefore the upthrust isn't enough for the object to stay on top of the liquid, and therefore it goes into the liquid. So yeah, that's how you calculate it. Just find out how much fluid is displaced and then find out the weight using the density, and then you get upthrust. Done, finish. Yeah, that's about it. The last point is just saying that for an object that's floating there and is in equilibrium, the upthrust of the object is equal to the weight of the object. So yeah, that's it, done, finished. Just use this information and then solve your questions. Just be as logical as possible. Just think in the most logical way. So yeah, when you're doing any force question, do write, if you're very unsure of what forces are going on, do draw your mass body diagram, or at least write down what forces are going on and in which direction, so it's easier for you to understand how to proceed with the problem. And if there's a moments question, then do take note of where all the moments are taking place, as well as the perpendicular distance, not just any distance but perpendicular distance. So this is where you end up messing up in your MCQ questions. Make sure it's a perpendicular distance. Yeah, I think that's about it. I think we're done. If you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye. Good luck for your A's, I guess.